Okay, great. So wrapping C code or C++ code in this case. Yeah, C++ code and Python code so that we can call them from a Julia interface. Whoever is familiar with Max, this is slightly similar. Like if you can write Max code and then you just go and call the function from MATLAB. This is in a way or another similar, but you don't have to rewrite your function. You just get the C or C++ function or Python function and then just call it as I'm going to show you. So we're trying to do Fibonacci. I hope everyone's familiar with Fibonacci. We're going to do the iterative version of it. There are multiple versions, but we're going to do the iterative version that is based on updating x and y based on the following formula, which is here. For convenience, the C++ code will look something like this. Anyone object to this? Okay, simple C++ function. Python code will look like this. If there are any objections, we can change the code. And the Julia code looks like this. So for I is equal to 1 to n. So I guess this notation is not really very nicely done. Okay, this is nicer. So we're going to start by running the Julia code. So run Fibonacci. Then we're going to say f is equal to 0. We're defining it. The reason I'm doing it 10 times is just to run the operation multiple times and see how much it's going to take on the 10th time. So I'm timing the entire for loop. F is 6765. We're going to see that the values are not going to change in other languages. And this is the time that it took. Now the Python notebook. So, okay, actually I need any Python experts here? Okay, okay. Timing, so tell me if this was a wrong way to time the Python code, because I wasn't sure if this is the right way. Time is not defined. Oh, okay.
So Python has a package called timeit.
Timeit?
Yeah.
If I import it to work, or do I try it offline? I can do the C++ code while.
Let me figure that out for you.
Okay, so I'm going to show you the C++ code now. So if we go back here, so the C++ code, I have created it and it's there in the folder if you want to use it. All you have to do is compile it. So compile and then run. And obviously the C++ code is really fast. And the value is 6765, which was the value in the Julia code. And
How did you time it?
I actually, so if you look at the C++ code, it's here. The timing, I really got this timing function from Stack Overflow.
That command, that would be easy in the shell. There's a time command in the shell as well.
I guess it wasn't time command.
Yeah, time a.add 20.
Okay. Is this the real one? No, the top one is my code.
Oh, okay. Which is equivalent to this one?
Well, the thing is, this includes time for setting up the Linux process, which could be not negligible. We're using CPU time or wall clock time?
Wall time.
Okay. So
Yeah.
that's the right time.
Yeah.
And are you sure that you're actually running all 20 iterations of the loop? Because compilers love that.
Sorry, I couldn't hear you.
Are you sure that you're running all 20 iterations of the loop?
Yeah, so if we go to the main, so this is not get wall. So we start by getting wall time and then for loop, call it 10 times, and then get the new time. Does that look right?
You might want to take this, so it's hard to know, is the compiler, if it's really smart, it could actually, oh, sorry, the A is read from the command line.
Yes.
It still could optimize out the 10 calls.
Only once, I'm printed again.
So a trick to avoid that is just to take a summation or something like that.
Oh, okay.
It can't. Well, it still could do it. But
Okay. Okay, so maybe the timings are not that fair.
you just have to look at the assembly code and
Okay.
actually see if it's got a forward there.
Okay.
I mean, the problem with simple benchmarks is oftentimes they show what the compiler does versus what the system does. But it's fine, just go
Okay.
ahead.
So let's not worry about the time that much now, but this is, we're running the Fibonacci. Now the goal of this is not to compare times, but it would have been great if we were able to compare times. But since things are different from each language, now we're going to do the wrapping of the function. Now let's start with the C++ code. So this is the function that is up there. It's really the same code. Just copy it and move it to a new file, call it another name, whatever you want it, and add the extern C keyword on top of it, wrap it with an extern C. Now, if this was C code, you don't have to do this. But since this is a C++ code, you want the compiler to understand it as C code, you literally just have to add extern C to the top and then wrap it with this close braces and semicolon. Creating the make file, it's not really, I mean, like there's nothing so fancy about this make file except that like these are the two lines that you should be. The first thing is running the C++ code. So if we do, I guess I can do make, or I can do I mean, it's G++ replacing this command with the C++ flags, which are here. So this is telling the compiler that compile this as C, so G++. And then...
There's a question.
Yeah.
If you change that O3 to O0,
Uh-huh.
it will disable all the optimization.
I wasn't running the previous one with O3 anyway.
Ah, okay.
Yeah.
So I think the thing to emphasize here is there's nothing that has any impact on Julia here. Like this is literally just compiling the C++ code to a shared object. That's all this make file is doing.
Exactly. So I really just wanted to explain these two. So this is literally just compiling, and the second line is creating this shared library. So since I'm running this on a Mac, this is going to be, the flag will be -dy_lib, and the object fibolib name will be extern c.shared lib extension, which is dylib in this case. So and of course this won't work, so I'll just do the make.
Dynamic lib. It's not dy.
Yeah. Okay, great. So we created the dynamic library, and it's here. So compile and then create dynamic library. If you're on a different system, this could be .so on a Linux system. So here I'm defining if OS is Linux, it's going to search for fiboextern.so. If it's otherwise, it's going to search for dylib. Now, once I defined my path, I can call this ccall function. What ccall does is that, first of all, it says, okay, what's the function that I want to call? And the function that we want to call is Fibonacci. I guess it used to be Fibo I. And the library path is the one I just decided on or defined. So I'm telling the code, this is the library that I created from this function. The return type of this function is, if we go here and we open the extern C version, I don't know how to, okay. Okay, anyway, the return type is an integer, so it's an int64. It could have been just an int, that's not a big deal. So the return type is int64. The input type is also put type is int64, so that's an integer. And now that we've defined the input return type and input type, all we have to do is pass the actual input, and the actual input is n in this case, which we've taken from here, and then return r. And that way we have a C++ wrapped function. If we just call it, didn't find Fibonacci because it was correct the first time. And now we have a C++ wrapped. So all we had to do is create the C++ code, compile it, and create the shared object, and then call thisccall function and know what to pass input to it. So function, library, return type, input value. Okay? Wrapping the Python code, it's really much simpler and easier, to be honest. All you have to do is create this Fibo function, or define it somewhere. So fibo.py. You have it on the GitHub repo. It's really just defining, it's the same code that we saw here. It's just copying this and putting it in a separate file. All we have to do is call a PyImport macro on it. So now we've imported it. This PyImport is part of the PyCall package, which now I decided to use. So if you're the first time using it, you have to add it by package.add. There's something that's a rough edge in PyCall. For some reason, it doesn't search in the local directory, and that's something that should be fixed. To fix this, currently you just have to add this line of code to tell PyImport to search in the local directory. Now it searched for it and it found it, and now all we have to do is really just call fibo dot whatever the function or method name was, and that's fiboiter, and that's how we imported a Python function. Okay, these are wrapping C++, wrapping Python codes. If you have more questions, I'm happy to answer them. Okay, I'm going to use the last 17 minutes really quickly to go over the last. So the folder number 4, which I'm not going to go over, is wrapping some more complicated functions, which if you want to experiment with it or go over it, you can email me or ask me questions whenever you want after. Okay, so some machine learning stuff. So 1, 2, okay. So this is a statspace.jl function, so library package that you can import or just add by using package.add and then use the using keyword. That's how you use it. If you create. Sorry, this is still base. So far I haven't added any packages. This is base Julia. You don't have to add any packages to get the mean, standard deviation, or variance. Statspace is another Julia package that has some functions, which, for example, describe of x can give you. So now it's compiling. So the first time you import a package or call it, it takes a little bit longer than usual. So
does RMath mean it interfaces with R, or in general does Julia interface with R?
No, it looks like this one does. I mean, Julia has many things that interface with RMath, but that wouldn't be the norm, right? Or
I think RMath just uses this set of math libraries that R has, so it just brings them into Julia.
Okay, so it does have a way to communicate with R.
There is a way to communicate with R too. So if you want code between R.
There's an R call function, just like right? I'm not sure, but
we haven't done as much with the R stuff.
Yeah. yeah. But I think there's, yeah, an rcall function. So stat space, you can describe x, get the geometric mean, get the z-score, which is m minus mu over standard deviation. So these are some cool things if you want to see them. Adding packages, so here we're going to use two packages, data frames and our data sets. The really nice thing about data frames is that it has the type or the value NA, which is in many data sets when you call them, or create the data, sometimes you don't have values. So this is usually sometimes replaced with 0, -1, depending on your preference or whatever. But in this case, there is an NA value. So you can.
Can you do the opposite thing? Can you wrap Julia from Python or C++?
I'm not a Python expert, so I don't know. There should be a way, I guess. I don't know.
So you don't really need to wrap Julia in the sense that it compiles to native code. So probably what you would do is you just, you'd have Julia compile to native code and then just call that from Python.
Okay. So A is of type NA. If we add A to anything, it's still going to be NA. The type is NA type. So that this is what data frames introduced. This is a simple data array. So if we're adding states, Indiana, Illinois, Michigan, and then we say, okay, what is this thing? It's an ASCII string of multiple things, except that one of them doesn't have a value. So it didn't really change the type of the array or the vector. It's still an ASCII string array, but one of them is an NA. We don't know what that is. Okay. We can do the same thing with numbers. This is NA. We can get the mean of something that has an NA, and the value will be NA. Now we can drop NAs, which is great. So there's a drop NA function that is automatic. Once you call a mean of a drop NA of numbers, it just drops them and gets the mean without that value. Now, sometimes you want to drop an NA. By dropping an NA, it means that as if that value doesn't exist. So the mean in this case, if we have numbers, it's really 1 plus 2 plus 3 divided by 3. Whereas if you want to get this value, which is 1 plus 2 plus 3 divided by 4, which means you're kind of assuming that NA is 0, you can convert the numbers, which was a data array, to a new array, but you replace every NA value with whatever value you decide here. So you don't have to go over each one of them. You can just replace it and tell the code to just do the work for you. So there's a difference between drop NA. So drop NA doesn't replace anything, just assumes that they don't exist. This is reshaping. So this is the numbers. We can start by a 2 by 2, and then so numbers were numbers were a 4 by 1 vector. Now we reshape them to 2 by 2, and then we can do matrix operations with them. So if we do this, NA numbers reshaped as NA2, 1, 3. We reshaped it to 1 by 2, 2 by 2, and if we get the matrix multiplication, it's NA, NA, NA11. So whatever number gets multiplied by NA was NA. This is a basic data frame. If we define a data frame as rows and columns, we're going to say these are the names, so names of the people. These are the ages, let's say. And now here we define a data frame where names is equal to n and ages is equal to a. And this is how it looks like. This is another data frame of the same people, except that we have their income here. There's a really nice feature of data frames that tells you or allows you to combine two data frames together. So there's the join operation, df and dff on names. So both of these data frames have the same one same field, which is names. So this is telling the code to combine these two things based on names, and it does it for you. So I guess it's, yeah, you can see it here. just to get the same. Okay. Accessing columns, you can access columns by symbol, or you can access columns by the actual index of the column. This is how you get it. So this is column 1 and this is column 1. Both of them are the same thing. You can describe a data frame entirely. So this is names data frame. It gives you a description. And then ages data frame gives you a column, gives you a description. You can, using the rdatasets package, you can call some standard data sets like iris. You can just call it by calling the function dataset of datasets / iris. There are multiple other datasets people can start with, but this is one of the famous ones. You can filter by, or say apply a function on iris by the species. So this is saying for each separate or different species, find me the mean of their petal length, let's say. You can do other things. You can do sum. It gives you the sum of their petal length. It can give you anything. What this means is that for each species, go find their petal length and find its mean, or find its sum, or whatever feature you want. So this is mapping. This is a map that we saw before. You have way more functions. There's mean of a column, median, head, head. So that's how you get the head of the function of the data frame. The head is usually defined to be the top 6 elements. Call-wise, so since this is not really a matrix, so you can't do sum of. So usually, okay, let me add one here. If A is equal to rand of 3 by 3. You can do sum of A across columns, and it give you a value. Since data frames or iris is not really a matrix, you can do the call-wise. So sum of iris, comma 2. It's going to complain. It says there's no sum defined on this thing, and there was no mean obviously, and there was no median, but it's defined in the function itself, in the package itself. So here you can do the call-wise. It says call-wise do the median over each of these things. Each column is understood as a feature, so that's why the call-wise function could be useful sometimes. You can also read table from a CSV file. So I have the CSV file in the folder if you want to read it. It automatically stores it in a data frame. And now, if you want to create your own data frame, I guess we did. Oh, if you want to write it, so you can output your data frame to an output.csv. So let's say we created our own data frame here. You can just write table to an output.csv and pass the data frame as input. And that would have should have created an output.csv function, or yeah, it's here. Okay. The housing example, I guess, have maybe 5 more minutes. So I'm just going to show you the really major features. These are some packages that the features will need. You can also read a table, not necessarily from your own local directory. You can call, you can use the package requests to add something from a URL. So if this is our URL, you can do read table of requests dot. Oh, great. Okay, this is running. So you can, in principle, read something from a URL. Okay, I'm going to do the smart thing now and ignore this for a second. You can look at the Python notebook on GitHub. It shows the result. This is how you call it from a URL. This is a basic plot if you want to see the plots of your values. This is a scatter plot that uses a pyplot function. Once we've plotted this, we observed that so many of these values are actually zeros. They don't have a value. We didn't. Their price was 0, so there's something wrong when the their square feet is 0, so there's something wrong. So maybe these values we don't have them. So what we can do is literally just drop everything that is less than or equal to 0. So we only keep the ones that are bigger than 0, and then if we plot it again, we get the correct answers. We can filter them. Sorry, we can get the we saw this function before, by, which gives us the summary of each of the features. I guess I'm going to skip this. What I was doing here is a k-means clustering. So I guess you can check the example offline, but if you have any questions for now, you can ask me. But a k-means, literally, all you have to do is just send your matrix X and tell it how many clusters do you want. And if there's this just a small tiny script to plot the clusters. This is the clusters that k-means got. And this is another clustering, I guess with different k. And this is a KD tree. If someone wants to get the close neighbors to a certain value, let's say k is equal to 5, and we want to find the closest values to it. And these are the closest. This is where it was close. So there's really nothing so sophisticated or compiled about this notebook. It's really just calling built-in functions. The fourth notebook is slightly more complicated since it fits a regression model to the housing prices. So what we have here is a set of houses, and it has beds and baths, and we have some more information about it. So we're trying to know what's the price of a certain house, given that it has whatever number of beds, whatever number of bathrooms, and whatever square feet is the area of it. All the details are in the notebook, so this is trying to fit a standard linear regression problem, so please feel free to go over it step by step. The fifth one has just literally really calling functions that are out there. So this example is another simple k-means example. It's really simple. If you want to start from it, you can do this one first. Which clusters the iris data set. You can do PCA. This is how you call the PCA function. And I don't know. OK, there's k-means and PCA here. So yeah. I'm sorry, I really wanted to go over more things, but I thought, I don't know, this would be enough for 2 hours, but apparently it's more. But yeah, feel free if you have more questions or other things. I guess I should show you the last few slides. In the terminal, you can always do question mark for help. So if you do question mark and then say mean, it'll show you the documentation of the function. If you want to switch to terminal, you can just hit the semicolon and say whatever shell command you want. And all Julia files are usually stored in .jl files. These are some resources for you, just a few. There's way more online, and this is me in case you want to reach out to me or contact me. And thank you. Any questions?
I have one.
Uh-huh.
For the last demo that you gave, the regression,
yep.
Is there also a Julia function for that instead of calling the Python version?
I didn't call the Python version.
Oh, that was a Julia.
The linear regression?
Yeah.
Yeah, that's all Julia code, yeah.
I'm sorry, I thought you were calling the Python function.
No, I only called the Python function in the Fibonacci example, and yeah.
Okay.
Anything for plotting?
Oh, did you think, are you talking about plotting? PyPlot?
That's probably what confused me.
Okay, so no, I actually, there's a comment about that. No, you're right. So plotting in Julia is still, there's so many mixed comments or mixed feelings about it. There are multiple packages that do plotting. People keep switching between one package and another. And I mean, from a personal experience, when I first started with Julia, it was really hard to start use a plotting package. All of them were, to me, not very good. Recently, there was this package that is called plots.jl. And what it does is that it has backends. So it's built on already existing plotting strategies or, I don't know, interfaces. One of them is PyPlot. Other things are Gadfly, if you've heard of it before, or Winston, or I guess there are a couple others, like 3 or 4 more. So my personal preference is plots.jl with a backend, which is PyPlot. And PyPlot is a Python interface, yeah. But there could be other things, yeah. Other questions?
So I noticed that this is for PyData Chicago, and I'm going to PyData.
Oh.
And I was wondering.
Are you a Purdue student?
No, I work here. I'm a data analyst.
Oh, did you sign up for PyData already?
Yeah.
Oh.
Yeah.
Because, okay, that's fine.
So I was wondering what talks you're looking forward to.
Oh, to be honest, I haven't looked, like I looked at the schedule really quick, like I saw there are a couple of interesting things, but I don't really, we can talk about that, okay. Yeah. Other questions?